Hello, good afternoon. Today I am discussing about structural equation modeling, which is a very important concept and it is often used by researchers in social science and management area. So without wasting much time, let us start with the presentation on structural equation modeling. The structural equation modeling is a popular and mature method to test theories. Structure equation modeling is also abbreviated as SEM, and it's a multivariate methodology. So there are multiple variables involved in this methodology. So why it is used for? So SEM it is used for this methodology used for representing, estimating, and testing a network of relationship between variables, and these variables can be either measured or observed variable, or they can be derived variable called latent variable or latent construct. So the goal of SEM, there are two goals. First, using structure equation modeling, we try to understand the pattern of correlation among set of variables. So there I told you two type of variables. One is independent variable and dependent variable, and these variable can be, or independent variable, these can be either observed or something that is measured, or something that is derived or latent variables. These are also called construct or variables, or some people also call them factors. I will explain to you later. And these are independent variables, which are also called measured variables, observed variables. Some people also call them items, yeah, or some people also call them either observations or measurements. So first is the correlation or covariance among them, and then to explain this relationship, that how much of their variance is explained with the model specified. And of course, when in this SEM methodology, we must define an optimal outcome, a finding that a particular model out of many possible fits our observed data closely and yields a highly interpreted solution. So we start define an optimal outcome, that there we say that this particular model fits our observed data closely, and then this hypothesis is checked using structure correction modeling. And while we checking this hypothesis, we also come to know about relationship between these variables, or in the relationship that exists in the model. So what is a model? Basically, I just you some of the people who are new to statistics must be wondering what. So a model is normally a statistical statement about relationship among these variables. So something, this relationship when written in statistical form becomes a model. And when this relationship I do a pictorial vectorial representation, then it becomes a path diagram. And when I formulate a statement about set of parameters and I state the model, then it becomes a specification. And there are two type of models which can be there in SEM using AMOS. AMOS is a SEM evaluation software developed by SPSS, and which is a software family under the company called IBM. So the first model is recursive. When A leads to B, these are cause and effect. B is caused by A and C is caused by B. So feedback is not complete in this model. You can see these are called recursive model. And but in some models, when A to B is caused by A, C is caused by B, and then again A is caused by C, the feedback is complete. These are called non-recursive model. So what is a SEM structure equation model process in general? So in general, as a researcher, when you want to make a structured equation model, so among the variables, so first you review that. Normally we review the particular theory that we want to test, and then we look at the research literature. We do a literature review to support some model specification. We make statement about a model, about a relationship between the variables and about a particular theory. We specify the model using statistical equations and the path diagram, and then we determine the model identification. If unique values can be found for parameters estimation, the number of degrees of freedom for model testing is positive, should be positive. Then we select, as a number 4, we select that what are the measures for the variables represented in the model, what are the different variables and how they can be measured. Then we collect the data related to the variables in the model. Then we conduct the preliminary descriptive statistical analysis conducted in terms of what is the scale used. Is it Likert scale? And normally when we do SEM using MOS, we are only looking at normally we are looking at the metric scale, and we are looking at normally we are interested in interval and ratio scales. Then we look at the whether the missing data, there should be no missing data. All the collinearity issues must be resolved, and any outlier from the data set must be taken care of, or we should replace the outlier value or delete the outlier value depending on what we prefer. So once the descriptive data cleaning and descriptive statistical analysis is there, we estimate the parameters in the model, and then we assess the model fit. Here we take help of SPSS MOS software, and then if the model fit is good, if it can be improved, we respecify the model, and then we interpret and present the result in terms of model fit, in terms of relationship between the different variables, the regressions and the regression coefficient. So all those results are reported, and to support a particular theory or to prove a particular theory. So when we just to say the particular thing in the same thing in a different way, we the SEM model, when we want to evaluate it, it is done in two. First is we assess the measurement model. So the first is assessment of measurement model, where the validity of construct or the independent variables or dependent variables, they are the validity is confirmed using confirmatory factor analysis. Where here in CFA we check all the construct, they do regression, they construct validity, and the model fit results. And once our measurement model that says that all the construct are valid, and then we go for structure model. In structure model, we normally looking at the cause and effect. That is a relationship between latent variables and the observed variables, and the cause and effect relationship between dependent and independent variable. And when we use most of the program, we use the maximum likelihood estimation method for model fitting program. When we try to find the model fit, especially in a software MOS, we use ML estimation. And in ML estimation, all the estimates are calculated at once. If the estimates are assumed to be population value, they maximize the likelihood, which is basically the probability that the observed covariance are drawn from the population, the expected covariance. So the likelihood of the like is maximized, that the observed variances that we are observing are as close to the expected variances. So one key thing when we do SEM, all these things will be clear when we look at one example, is evaluation of model fit. Normally, I told you besides CFA, we also do the model fit evaluation when we make structural equation model, and we always using a SPS spaces MOS, we check the model fit. And basically in SPSS we say uh, like whether the predicted, how similar the predicted data are to matrices containing the relationship in the actual data. So the basically we say that in evaluation we normally start with the null hypothesis, that our model actually it is fitting the population perfectly. And but whenever we have this sample data that we have taken, and we try to fit our model, when we test it on sample and we say whether it is really, you know, whether it is really fitting that population, the data, it will meet the same relationship, will the model will stay true in the population actual with actual data as well. And normally this null hypothesis that the model fits perfectly in the population, so you normally do not want to reject this null hypothesis. We want this null hypothesis to be true. So when we do, the chi-square probability should be greater than equal to 0.05. P-value should not be statistically significant. So p-value should be more than equal to at least 0.05. It should not be less than 0.05. It should be more. Yeah. So when we do a structure equation model, we want to report the model fit, whether this model is fitting the sample data, and this will hold true in population data as well. So we normally look at first matrices we report is chi-square, uh, which describe the similarity of the observed and expected model covariances matrices. So basically it says that what is observed and what is expected model, uh, the covariances matrices, if they're similar or not. So one thing is this ratio of chi-square to degree of freedom. This value should, the ratio should be less than equal to 3. So normally this is preferred, but in some cases it's up to 5 is also accepted. Then there are goodness of fit indices. These are called CFI, NNI, and NFI. We will look at the definition, the detailed definition later on. So these goodness of fit should be, ratio should be zero point 0.9 or more than zero point 0.9. Maximum, of course, it can be up to 1. So normally we are looking at zero point 0.9 or more. Root mean squared error of is RMCA. This ratio, it's indicates the amount of unexplained variable or residuals. So this value, RMCA value, should be less than 1. And then SRMR, square root mean residual value, as should be less than 0.08. So normally we will report any three. So one can look at, normally we will look at this and one of this, let's say CFI, and then we'll report RMCA. Some people will also, beyond three, they will also go and report the fourth ratio of SRMR in their report. So what are the assumption in structure equation model? Basically, when we do SEM and there, it's suppose multiple variables are there. So of course these relationship are, when you look at in terms of statistics, they are normally represented, you know, in terms of in the matrices form, of course. But I'll not go into this. So this is but we are here, we are looking at linear relationship. So this thing basically is that between different variables we only look at linear relationship. So non-linear relation, then we better stick to other methodologies like neural networks, but here we use linear relationship only. We use metric data, could be ratio or Likert scale. We are not looking at categorical variables. Uh, then we assume that these variables are normally normal distributed. Then we are looking at in a particular construct or a particular dependent variable, latent variable. There should be minimum number of statement or items or observed or measured. So in a particular construct, there should be statement, there should be minimum 3. Some people say 2 is enough, but normally in literature, when we do it, when we look at expert opinion and empirical studies, normally they look at minimum 3 statement linked to a latent variable or a construct. Then of course they're looking at minimum sample size. Some people say minimum 150, some people say 200, 300. So normally how big is sample adequate for your study is determined by the KMO calculation. This KMO can be easily calculated using SPSS. So when you open up SPSS MOS 5 software, this is what the, when you start, this is what it will look like. And so on top, you, the top ribbon, you will see some of the options available, and then there are different shapes that you're seeing here. Like for this shape is for observe, this is for latent, and of course this is for the variables in the data sets, and you'll see all the different things. These things can be drag and drop. This is this screen is your actually where you will work on your project, or this is the screen where you will work on the model. So you can grab the different shapes or different uh, arrows from here to here, and you can work here. So let me, this is just to give you an idea. Yeah, and you will normally see three colors, four colors here. One is green, blue, black, which is the default, and the red, that's where the action will be executed. So when you start the spaces amos, we will actually start work on it right now to give you an hands-on example, and then I'll explain more to it. So when you, there's some symbols similar to what I explained here. There's some symbols here, and what does these symbols mean? So when you see a rectangle, it's basically a measured or observed variable. When you see a oval shape here, then it talks about unmeasured or a latent construct or a factor. Yeah. So these are basically the three different names. And the arrow direct relationship from here to here is, these are by the arrows, and the covariances or correlation is by the double headed arrows. Whenever there is any measured variable, it will, you will normally see an error term which is associated with it, and the way you is a small circle with e written it, and then an arrow that is coming to an observed variable. And of course whenever you have any one thing which is not shown here, whenever you have any arrow that is I'll, when I explain the rules, I'll tell you. Whenever some arrow is coming to into any variables, so all the dependent variable must have an error term. Let me quickly show it to you. So these are the few rules. So I just explained to you there are two types of variables, observed and latent. Observed are shown by which are directly measured from the respondent, also called items or uh, measured variables or statements. These are shown by a rectangle, and latent variables, these are inferred indirectly or represented by the oval shaped. Yeah. Rule number two, dependent variables and dependent variable. Dependent variables are also called endogenous variables, and these variables normally will have one arrow toward them. Suppose this is a dependent variable, and invariably you will have one arrow which is toward them. Exogenous independent variable are also called exogenous, and something which is, suppose this is an independent variable, it will have and one arrow going out from it. So this is the normal way you represent independent variable which are exogenous and dependent variable which are endogenous. So any observed or measured variable or any uh, latent variable or construct can or factor can be dependent variable, dependent variable. So you see these two are two observed variables. Yeah, so this is dependent, arrow coming into it. This is independent. Here you will see this observed variable is independent, but this latent variable is dependent. Here you see this, there may be an arrow coming here. This is independent, and then observed variables in dependent variable, and latent variable is independent. And then here you'll see independent variable as well as dependent variable, both are latent variables. So one rule number 5, which is, so whenever you have something like this, so it is not shown here, but it requires, it must have, if this thing is there, then it must have another independent variable, sorry, or an measured variable. So if something like latent is there, it should have one of these two along with it. And whenever you have an error term, suppose this is the relationship and you have an error term here, so in SPSS we normally give them the regression weight of 1, right? And suppose here we have, rather than this, let's say there are two observed variables or two statements and one one latent variable. Then one of these regression weight we normally put equal to 1. This is when we do the model evaluation fit, but we'll come back to it later. So just I said before, each dependent variable, and how we say something is dependent variable, normally you will see an arrow which is coming into it is a dependent variable from the other variable, some, and each dependent variable must contain an error term. So you see this is dependent, and then it will have an error term, or sometimes we call it residual, that must be associated with it. So here you see incentive motivation is caused by incentives, and then there is a dependent variable, you see an error. Then you see performance is caused by leadership, you see an error. You see motivation is caused by leadership, and there's a dependent variable, there's an error associated. So key steps in SPSS Amos, let's look at. So we will here, earlier I told you about SEM. Now we will do SPSS using Amos. So we launch Amos graphics. We attach so when we attach an SPSS data file, normally they are with the extension SAV, and once that SPSS data file is attached, we create a new model graphical representation of it. We specify what is the data file that is attached to it, what are the different variables. Yeah, we name those variables, we draw the relationship, correlation, or the cause and effect arrows. We alter the appearance of part diagram if required so that it look proper. We constrain a parameter in terms of error regression path coefficient being 1 and one of the relationship between dependent variable and independent variable, one of the regression path diagram, one of the relationship, the regression coefficient is set to 1. We perform the SEM analysis, then we view the text output and graphic output. We print the path diagram showing the standard estimates, and we copy the text output with the fit indices data. Now let me, whatever I just told you, these key steps in SEM evaluation or SEM analysis using AMOS. Now let me show you, before we start, I want to give you that in the measurement model, we have to do CFA. There are multiple level of CFA. So when you have, suppose this is dependent, this is latent variable, and then this is observed variable. And this latent variable is linked to these observed variables. Yeah. So if something is latent, you will, and these are observed variable. This is the normal typology, the how it is shown. And something I told you, something is dependent, it must have an error term associated with it. And here this is level 0 order CFA. This is first order CFA, where you see two latent variables, and these latent variables, they are dependent on, yeah, there's a relationship between this first order CFA. So I told you, whenever there is an arrow coming into any variable, any construct, it must have an error term. So this arrow coming inside, so there is an error term here. This arrow coming here, there must be an, so yeah. And I told you, whenever there is a latent, it must be, there's another latent construct should be there, or there should be an observed variable here. So you can see arrow coming in, error term, arrow coming in, error, and all these values, all the error term, the regression coefficients are set to constraint to 1. And you see this relationship between latent variable and the observed variable. So out of these four relationship, one regression path coefficient is constrained to 1. So in MMOS you have to make sure that this thing, so you can see here what is set to 1, it is set to 1, and all these E1 to E10, E12, all the error term, the regression path quotient set to 1. And sometimes you have second order CFA. So this is 0 order, this is first order, and when you see here, this is second order. So 0 order, first order, and this is second order. But still it is confirmatory factor analysis. This shows how the latent construct or latent variable and observed variable, how they are related to each other and how they are derived. But cause and effect relationship are shown using SEM. So you see a little bit of difference here. Yeah, this shows how the different construct are derived, but cause and effect relationship. Now here see tangibility, empathy, service quality depend on is derived, service quality derived out of tangibility and empathy, but service quality leads to, so this is the satisfaction is caused by service quality, which itself comes, this is a latent, service quality is a latent variable which itself consists of tangibility and empathy, two other latent variables, and these two latent variables are themselves observed come through S1 to S4. 4 tangibility come through 4 observed variables, and empathy again come from S5 to S8, 4 other. Satisfaction, which is a latent, which is measured by S1 to S4, which are observed or measured variables. Uh, of course, these error terms. So let's look at one example. There's a thing that a knowledge and the value and the satisfaction leads to the performance of an employee. Correct? So in this model, we have variables. So observed variables are performance 1, performance 2, knowledge observed variable are knowledge 1, knowledge 2, value is observed value 1 and value 2, satisfaction is measured by 1 satisfaction, 2 satisfaction. Yeah, so this is how different thing. And performance is 12 item, subset of role performance. Yeah, past training variable is not included in this. So let's look at one example. We are using the data set. It's called warren.sav. This is SPSS data set with no missing values and no outlier, and all the relationship are linear, and variables are normally distributed. So we'll see how we can get standard estimates and estimate, and we also look at the model fit. When we talk standard estimate and standard estimates, these are about the regressions. So you can see knowledge, which is a latent variable, is caused by observed value knowledge 1, knowledge 2, and of course value, which is caused by value 1 to observed value, value 2. Satisfaction is again a latent variable, satisfaction 1 and 2. Performance is a latent variable measured by through 2 measured. This latent variable is consist of performance 1 and performance 2, which are observed variables or measured variables. Yeah. So let's look at how the data look like. So we will go to SPSS and see. We have opened up a data set called warren.sav. This is how it looks like. Yeah, what I explained to you just now. So we're gonna close it here, and we will open up. Okay, I can draw here very easily. I could have actually, just to show how the things work here, I can actually. You can see here, once you bring it here, you bring it to a particular size, and when you're okay with it, you just, and again, one more. And suppose you want dependent variable, yeah, you can, and it is fairly easy drag and drop to work on spaces MOS, and you can select the data file also. So let me actually, fairly easy and intuitive to draw the model, the graphical model, and I have one model already ready which I wanted to show you. So this is the model we are talking about, related to the spaces warren.sav file that we talked about, and easily drawn. You can see the error terms, one of the all the error terms, the regression coefficient set to 1, and these are the model parameters. The values are set to 1, and we will we can view what are the different variables in the data set, which can be seen from variables in the model. You can see error, all the error terms, knowledge 1, performance 1 and 2, satisfaction 1 and 2, value 1 and 2, and you can see the variables in the data set, which are also performance, knowledge 1, value 1, value 2. So you can see all the observed or the measured variables in the data set, and how to, so first I think is we look at data file. So of course you can select from here file name, we go to desktop, we have for warren file here. We can actually view the data, but we select, say, okay, yeah, and then, so something that I always like to, variable, when you say name unobserved variables, so anything which error terms normally which are difficult to name are named here, and then to do the analysis, when the data file, you just click on this button, or no, there's an error here. Sorry for the confusion. I think we opened up the model. I opened up the model B, which is basically I constrained all these things so that we can do comparison of both the model. So we come back to, for this demonstration purpose, we have model A. So same thing as explained before, only one of these regression coefficient, it is constrained to, coefficient is constrained to 1. Yeah, and I will see the data file, which is Warren. It's okay, and I look at, okay, all the variable in the model, in the data set, also all the variables are correct. And once this thing is done, I do the calculate the estimate. So once your estimates are calculated, yeah, you will see this red output part diagram. It comes to life, and when you click here, you can see, yeah, all the, this was set to 1, but this was 0.68, this was set to 1, this 0.76. All the path coefficients come in, the r square values are also shown here. Yeah, for these latent construct, all these correlation coefficients, they are also shown here, and cause and effect relationship is given here, and you can, yeah, chi-square value, which is 10, p point, oh, it's of course 0.73, which is more than 0.05. And normally we are more interested to see the standard estimates. So when we click on standard estimates, so you can see these beta values here, 0.7, 0.65. Okay, most all of them are more than 0.6. That's good enough. Okay, a little bit correlation is there, but it definitely less than 0.7. R square value is 0.66. That is good enough. All these coefficients are shown here, and we can, so this is the graphical output. We're looking at standard estimate. That's what we are interested in, but we can also see the, read the text output here. So you can see this is the same thing. Today's date, we conducted this exercise. Models recursive, of course. A, C depend on B, B depends on A. It's a non-looping relationship. All the observed endogenous variables are shown here. Unobserved exogenous variables are shown here as well. The total variables in the model are 21. Numbers of observed variable 8. Number of unobserved variables are 13. Exogenous 12. Endogenous 9. Degree of freedom is 14. Chi-square is 10, degree of freedom 14, probability 0.7. So you can see, so first thing, normally we will look at the model fit. So this is chi-square by df point. It's also called C-min divided by degree of freedom. You can see here it is less than 3, it's 0.738. Then we look at goodness of it, indices. So RMR GFI goodness of it index. You can see RF GFI is more than zero point 0.9, which is good enough. CFI is 1, which is also very good because it should be more than zero point 0.9. Root mean square error is zero point 0, which is also good. Yeah, so this is good enough model that gives the goodness fit index is there, and we can also look at uh, the regression. And when we look at, of course, the maximum likelihood method is used, we are looking at standardized regression weight. That's what we are interested in. So performance 0.56, 0.130, performance to values 0.38, satisfaction 0.73. Yeah, so these values are pretty good, except this value, which is satisfaction to performance and value to performance. These are a little bit on the low side. We are also interested p values here, the regression weights, and you can see probably, yeah, from here also we can see some. This is, we want all these p values to be significant, so only these value is significant, knowledge is significant. So there's some issues here. Value to performance, this is significant, probably this is also significant. So they were doing here 0.001 level. So if you look at 0.05 level, probably then these two probably are something that are not significant. Otherwise all the relationships are significant. And this is how you will read a particular model. First, after the fit, then you look at the standard regression weight, and then you look at the regression weights of the default model, and you look at the p-values. It should be more than 0.05, and all these value in the regression weight has to be less than 0.05, and then you report these. And for the standard regression weights, that's what the standard regression weights are reported. Okay, when we do the regression analysis, probably what I could have done is I could have in analysis properties, we are using estimation as maximum likelihood, so that is good. Fit the saturated independent model, that is good. One thing we can always look at modification indices, and we can set this value to be 10 here. Bootstrap is fine, everything else is fine. And when I run this model again, and when I look that So you can see we also see the modification indices here. And if we want to improve this model, then yeah, it's we are not getting here, but normally because this model is very good fit, and otherwise we'll get modification indices, and it can be used to improve the results. And normally when we want to improve the results, so when first thing we always try to do using the modification indices, one of the thing we can do is we can improve when we correlate the errors. So this action in the same they have to be in the same construct, and for these object variable when the error terms are correlated, this will improve the model fit in basically in terms of C min divided by degree of freedom, that can be improved, and CFI level also improved. Second action we do is we can improve the conversion validity. So if we can improve the outliers, it will also basically help improve our model. Third is in terms of discriminant validities. So if by removing the cross loading, we can improve on the discriminant. So these three actions are normally performed beside increasing the sample size. These three action, which is correlating error in the same construct, improving on convergent validity by removing outliers, and improving on discriminant validity by removing cross loading, are normally done to improve the models. So that's all about structure equation model. Thank you very much.